Hey guys, so welcome everyone to this new session, this open lecture by Diego Apellániz, where he will explain some cool stuff that he developed. I would say that in using the foundations on top of the Grasshopper tool mainly, maybe some other stuff, I don't know. So he's a civil engineer from the Polytechnic University in Madrid. And he has worked in several engineering firms such as Bollinger+Grohmann or Fhecor Ingenieros. And he has a wide portfolio that involves both engineering and architectural practice, but also a developer background that I would say that it's really interesting. So I think that it's been like a year or so that we were discussing with Mark some cool stuff on life cycle assessment. And he just said, look, I know a guy called Diego, really nice guy, an expert in the field that you could welcome in the program. And you are here. So welcome, Diego, and feel free to share your screen. And thanks for accepting our invitation.
My pleasure. Thank you very much for your present introduction. And now, let's see if this works. So, are you watching my screen right now?
Yes.
Okay, perfect. Yeah. So in this talk, basically, I'm going to explain some workflows or some research that I've been doing about these three topics: sustainability, structural design, and machine learning. But before we start into it, let's just let me just complete your introduction with some pictures. So basically, I have two workplaces right now. On the one hand, I work at the Berlin University of the Arts at the chair of structural design and technology for the Architecture Institute, and we have several research projects here. But yeah, all of them are basically focusing on researching new structural systems or new digital workflows, let's say, to build with less carbon footprint and also using structural elements. And we are going to see some of these projects later on in more detail. And on the other hand, I work, well, I've been working at Bollinger+Grohmann for 5 years, but since November, I work at this new company, the EDD Holding, Engineering Digital Design. And well, basically, in this an engineering office as well. And they also try to implement digital workflows to work more efficiently, of course. And until now, they've been working with Revit and BIM360 and Autodesk Forge and so on. But since I'm here, we've been using Rhino more and more. And yeah, basically, this is my two, let's say, lines of work. But now let's jump into the presentation. So the idea is, okay, I'm going to talk about these three topics, but as Gerard said, the let's say the connection or the interface between them is parametric design. So I thought that let's start with an introduction. Maybe the first slides are going to be a bit simple for some people here, but don't worry because it's going to get complex really quick. So be patient. And well, as most of you know, what is basically a parametric design in this slide. I'm showing the interface of a Rhinoceros on the left side. Rhino is this 3D modeling program, and there is a plugin for Rhino which is Grasshopper, and Grasshopper is basically visual programming environment in which we can create algorithms by connecting these boxes or components, and with these algorithms we automate tasks in Rhino, such as the creation of these relatively simple geometry objects that you see on the left side. But the thing is, what I want to explain here is that these little components are, each of them is basically one algorithm in itself. So if you take a look into the second script, we are taking two curves as input, and then the first component or algorithm is dividing these curves into several points, and then we are connecting these points to create arches and so on and so forth. So when we talk about parametric design, in 99% of the cases, is also basically algorithms aided design, and we are going to be using this concept in this presentation a lot. So basically, let's start with a historic evolution, because I think it's important to know and to realize where we come from to see where we are going with this with our research. So we have these three buildings here, and I'm sure that all of you know them, but I just want to explain the role that parametric design played in these designs. So the first one is the Guggenheim Museum in Bilbao, and in the 90s there was already this interest and to try to achieve this kind of complex geometries. And this, of course, this building from Frank Gehry is a good example of it. But at that point, there was no available software that was designed to work with such complex shapes in architecture. So with the office of Frank Gehry, what they did was basically to use the software CATIA for structural design, for aeronautic design. So they were using some tools outside of our sector. And then, but 2 years later, we have, for example, this example of the BMW bubble in Frankfurt. And in this case, the architects were using the software Autodesk Maya, that if you know it, it comes from the animation industry, so it's not for architecture either. But the engineers, Bollinger+Grohmann, they started using the first beta version of Rhinoceros, which is now more intended for buildings, right, for architecture, and these complex geometries. 1 second, sorry. And yeah, and finally we have the roof of the British Museum that was created in the year 2000. And I don't know if you know it, but this geometry was created by a guy called Chris Williams, and he basically wrote a script, a program in C++ to create this complex geometry, right? Because it could have been very, very tedious to do it by hand. And now this is basically the first steps of parametric design or algorithm design as we understand it right now. And of course, later on in 2007, Grasshopper came out, which made it very easy for people to do that, because now they don't need to write these programs anymore. They can just connect these components, and it's very easy. And also later on, the plugin Karma 3D for structural design came out in Grasshopper, right? So it made possible to create these kinds of complex structures that they were not possible anymore. And here you can see two projects from the office of Polytechnic, in which yeah, you can see how they design not just the let's say the appearance or the shape of the building, but also its structure with such yeah, parametric algorithms. And now at this point, this is the some script with the already mentioned Karma plugin for Grasshopper, and this is an interesting paradigm change in my opinion, because at the very beginning, if you remember the two scripts that we saw, we were just dealing with geometry, right, with points, curves, and so on and so forth. And and in this point, now we are not dealing just with geometry anymore, but we have something, the so-called objects, right? Because for instance, we have here a load, a support, a cross section, and its object have different properties, like for instance the force value, the position, and things like that. And it allows us to not just deal with geometry as before, but with many different topics. And this principle of using Grasshopper not just only for dealing with geometry, but with other topics, using the so-called object-oriented programming is the idea that we're going to see in the rest of the presentation. So I hope everything is clear so far. And now let's start with the first main topic. Let's see, which is a structural design. And basically, well, I've called this chapter Enhancing a Structural Design with a Parametric Finite Element Toolbox, because this is the name of one of the three Grasshopper plugins that I'm going to present today. And this plugin is already, I developed it, and it's already available in Fhecor Rhino. And there's also, we wrote a paper about it in collaboration with my former colleague, Robert Findlinger. And yeah, I developed this plugin when I was at Bollinger+Grohmann, and the idea was basically, okay, we have the plugin Parametric for Grasshopper for structural design, but sometimes in the office we need more complex calculations because there are some complex materials or some complex structures that require, let's say, some very complex checks or calculations. And for that, we require, let's say, a commercial finite element software, like an external program. And in this case, that program is RFM5. And with this plugin, you can connect Grasshopper and Rhino with RFM. And we are going to see some workflows and examples with that. But basically, if you are interested, this is how you developed a, a plugin for Grasshopper, right? Because in Grasshopper, you have their standard components, but you can also download external plugins for additional functionality. And you can also develop your own plugin if you're not satisfied with what there is out there. And what you have to do is to learn a programming language. In this case, I did it in C#. You can also learn Visual Basic or Python. And you create this let's say, this monster with a lot of classes and a lot of lines of code. And you compile it into this, let's say, intuitive user interface or Grasshopper plugin, so that each of these big algorithms here in Visual Studio, let's say, C#, is one simple component in Grasshopper. Okay, so now we have compiled our plugin. It looks like this, but what can we do with that is the next question, right? And basically, there are two main workflows with this plugin for structural design. We can either take, let's say, information from Grasshopper to the calculation program RFM. In this case, this works similarly to Caramba. Also, the user interface of the components is similar to Caramba because I took a lot of inspiration from them. And yeah, basically you are defining some geometry here, in this case, a simple line, and then you go to this component of my plugin and you convert the align into a beam by assigning certain properties to it. In this case, I just specify the cross-section number, which is already defined in the calculation program. And once you have your object created in Grasshopper, in this case, it's just a member or beam, but you can create everything that you want to, basically. I mean, from structural objects to load combinations and everything you want. And then you import that into RFM for some complex calculations. And not just complex calculations, but also if you want, there's like a tech engineer in the project, right, that needs to review your calculations, he's going to ask for a commercial software like this one, RFM, so that your project gets approved, your calculations get approved. And the other possibility is basically to import data from the calculation program RFM into Grasshopper in case that you want to analyze that, to check some things, to see how the geometry looks like. And this can also be very helpful, as we are going to see. And now some examples, all of them from the office of Bollinger+Grohmann, I think. Actually, this is the first project I used the plugin with. And the idea, basically, well, besides of the project itself, is that with Grasshopper, we cannot just deal with very complex geometries and very complex projects, but it can be very useful for basically all kinds of projects. And in this case, it was a building renovation. This is a skyscraper in Berlin. And well, there was a renovation because it was a former office building, and the new owner wanted to create apartments because he was going to make more money out of them. But he wanted to add new balconies, and then that led to additional loads. And long story short, we needed to reinforce these massive steel beams that are 5-meter high. And for that, we needed to design very carefully these reinforcements here, which are additional steel plates. And the modeling process is very complex in RFM. This is the calculation program I've been talking about. So I started developing this plugin in Grasshopper so that we can try out different designs and different shapes, and we can very quickly export them into RFM for some calculations and checks. And well, I shared it with the remaining colleagues at Polytechnic and then they liked the idea. So it was very interesting because then it was not just me using this plugin, but my colleagues started to use them more and more. And these are some projects that they used this plugin at. And the interesting idea is that I was not involved in the projects, well, maybe for some consulting, but my colleagues did it on their own. So this is very important also, that you develop a tool that other people are able to use, right, without your help. And in this first project in this Leipzig, the Red Bull Arena in Leipzig, the idea here, well, of course, we have a complex geometry, but we have this complex foundation here with the so-called piles and with different inclinations in each case. And basically in Rhino, it is very easy to draw a micro pile, but in the calculation program, it's very, very difficult because you have to specify the inclination angles and other properties. So with my plugin, it was very easy, and you could check that you are not, let's say, colliding with the existing structure very easy. So that was very helpful. And then we have this Tondo bridge in Brussels, of course. And in Rhino, you can very easily, let's say, trim and connect all your steel plates so that the calculation model is going to work in the end. And also, you can use this workflow, as I said, from RFM into Grasshopper in case that you want to create some interesting renderings like here, so that yeah, we can create some nice visualizations, right, for our reports, for competitions, or something else. And also, this is the project of the first slide. And in this case, well, the pavilion was originally in an exposition in Frankfurt, but exactly, but it's basically a grid cell of plywood elements, right, of timber. And the interesting thing of the project, well, is that the cladding is mycelium, like an organic, let's say, mushroom. And it was very interesting and very sustainable. And of course, the structure needed to be strong for the exhibition. And the fire resistance needed to be checked and so on and so forth. And with the plugin, this is very easy because we have different inclinations and different orientations. And with Grasshopper, this is much faster than doing it manually, of course. Yeah, I'm sorry. The weather in Berlin is not doing good things to me. Okay. And finally, the last workflow I wanted to show is, of course, optimization processes, because we can just deal with geometry, but also with results. And yeah, exactly. You know, maybe these optimization solvers in Grasshopper. So we export the geometry from Grasshopper to the calculation program, and then we run the analysis. We take the results back into Grasshopper, and with these solvers like Galapagos or Goat, we can optimize our geometry so that we come up with the, let's say, most economical structure, similar to the Caramba plugin, but now with a, let's say, commercial, an external calculation program. And to conclude this first chapter, I just wanted to say this is quite funny for me because I developed the plugin for RFM5, this program here. But of course, this is an independent program from a commercial distributor, which is called Global. And at some point, they said, okay, we are going to upgrade RFM5 for RFM6. And apparently, they liked my plugin so much that they ended up basically copying it for RFM6. So you can see this is the component. These are the components that they developed, and they look exactly like the same like my components here. And yeah, so I mean, but they talked to me beforehand, and they, of course, they said nice words about me, and it's some publicity for me, so I don't have any problem with that. But in the end, at some point, people are going to stop using my plugin and move on to the next version of RFM and the plugin of Global. But that's okay for me. And yeah, that's basically the first part of the presentation. The second chapter focuses on life cycle assessment, as Gerard and Mark were discussing, and how you can combine that with parametric design. But well, first things first, what's basically life cycle assessment? So, as many of you know, we are in a current climate emergency because the CO2 emissions and, well, basically the global warming, our temperatures have been rising exponentially in the past years. So it's clear that we need a strategy to fight against that. And furthermore, the construction industry is responsible for 38% of these CO2 emissions. And one of these strategies that we can use is life cycle assessment. So life cycle assessment, or LCA, this is a methodology for assessing environmental impacts associated with all the stages of the life cycle of a commercial product, process, or service. And this is very nice, but it's actually a quite, let's say, time-consuming, or exactly if you are doing this by hand, because life cycle assessment, basically, it requires you in your project first to compute all the material quantities that your building has. And second, you have to map these quantities to some materials. So you need some database of materials with CO2 values associated. And now you can map this database to your, let's say, elements of your project. And in the end, you can come up with the total environmental impacts or carbon footprint. But you need those two things. And as I said, if you do this manually, it's time consuming. So the idea could be, okay, but we have a 3D model in Rhino already for our architectural design or structural design. So why can we not use this model already to compute the material quantities and even run the life cycle assessment to get our carbon footprint? So, okay, now we have the we have our and of course, if we do this efficiently, we can implement this in the early design stages, because the design team will not have any problem with that, and we have more chances to influence our project, right? So that was our first idea, and so we say, okay, now we have the Rhino 3D model. It's relatively easy to get our volumes, our material quantities, but now we need a big database of materials so that we can compute the total carbon footprint of our building. And for that reason, we, well, basically, I went to 1GLCA. I don't know 1GLCA, but I don't know if you know this company, but basically this is a Finnish company, and they have developed a software for life cycle assessment. And it is a great software because it has the largest material database in the world for construction materials, let's say. And they already have a software, as I said, which already runs, but through their website. So you have to log it into their website, and then you can introduce basically manually or your material quantities and select their materials. And then you can run your life cycle assessment there. And what I suggested to them was to, okay, we have your wonderful software, but now if we can connect your software with Rhino and Grasshopper, we can also take the material quantities from our 3D model, and there are a lot of people who already work with Rhino and Grasshopper that are going to use that, yeah, like more and more. And they liked that idea. So we ended up, well, I ended up developing these plugins for Rhino and Grasshopper. And well, that was in 2021 in January, but we uploaded them into Rhino, Fhecor Rhino, like 6 months ago. So yeah, you can now download it. And another important thing is that QuantityLCA, so you need a license to use this software to calculate your carbon footprint, but that's for basically professional offices. And since this year, they are going to make that free for education, right? So if you are interested in using these plugins or this tool, you can write to them now, so that they give you a license. I guess if you justify that you come from a university, but that's big news in my opinion. So now let's explain how these plugins work. So on the one hand, one second. On the one hand, we have the Rhino plugin. This is a plugin basically for people that are no Grasshopper experts, so they can intuitively run a lifecycle assessment with this 3D model. And the Rhino plugin is basically this user interface that I have developed for Rhino. And you can see how you can map, let's say materials from their database into the Rhino geometries. And in the end, you end up with your carbon footprint in Rhino. And more interesting, in my opinion, is the Grasshopper plugin. And with Grasshopper, you can basically exactly define a lifecycle assessment in a parametric way. So we take as input either a Rhino model or a parametric Grasshopper model. And first we select our material from the database, as you are seeing here. Then we assign this material to our geometry. And finally, and next we have to create the so-called constructions, which means that we have to assign a class to our material to say, okay, this is a slab, this is a column, or this is a window, and so on. And we can also combine different materials. For instance, we may have reinforced concrete, and that's two materials. So we can combine them into a single construction, and in the end, we have just one result in the end, which is more, let's say, clear to understand. Then when we have our constructions, we run the life cycle assessment, we get our CO2 values and other impacts, and then we can visualize these results in the random viewport, which is something like that. And this is quite fast, and we can change this geometry, use different designs, and this is very easy. And that's basically the idea. And yeah, and those were the workflows. And now I'm going to show some case studies that we use these plugins at. And yeah, exactly. And all these projects are from Bollinger+Grohmann. So let's start with this one here, the Voltaion project. This is a new office building to be built in Berlin. And the approach was the following one. So the first step is to compare different alternatives, but of course it's not smart to compare different alternatives of the whole building, right? Because if you want to model 3 complete designs from scratch, it's going to be time consuming. So for this first stage, it's advisable to focus on a local model, right? As the one you see in the middle. And you can do some variations with that, right? Because it's smaller and it's easier. And furthermore, it's not just a local model, but what we did is to let's say add a new component for the previous Grasshopper plane of structural design, as I said. So the thing is that if we want to run the life cycle assessment, we need the precise quantities of our materials. And for those quantities, first we need to do the structural design. So now you're going to see the first interface between these topics. So the idea was to first calculate the structure in RFM, in the calculation program. And then with this component for my previous plugin, we can export not only the material quantities, but also the material names that we are using in our calculation model. So in the end, we can basically with one click get the carbon footprint of our structural model. And with that process, we created 3 different design options, 2 of them in timber and another one in steel, exactly the third one. And of course, we can compare the CO2 values, not only the carbon footprint or global warming potential, but also the CO2 that is stored in these timber materials, which is also very very positive for the environment because you are, they say, sequestering CO2, and that's also helping against global warming. And not only that, but you can also combine this plugin with other Grasshopper plugins, in this case with Octopus. I don't know if you know Octopus, but this is a plugin for multi-objective optimization. And in this case, what we did was to optimize this structural system in terms of CO2, but also in terms of price and well, structural behavior displacement, so that we tested different, let's say, geometric configurations, dimensions and distances and things like that to come up with the most efficient solution. And once we are satisfied with this preliminary design, then we jump into the global model. And in this case, well, the first step was, of course, in Grasshopper because we're trying different things using other plugins, and this is faster. But once we know the topology that we're going to use, we can jump into the global model like that. And for that, we can use the Rhino plugin because the process is let's say, more manual, more analogic than in the preliminary study. So the Rhino plugin was good for that. And this is how the global model looked like. And once you are ready, and once you have your let's say, carbon footprint of your building, what you can do is to compare your result with the so-called benchmarks. So the benchmarks, in this case, the benchmarks of molecules are these levels that they have, let's say, developed. And according to your building type and to your region, you can see your score, right? And in this case, we scored a B, and the people, the other team, the design team was happy with that. So we moved on with the project, and everything was fine. And now another project. I'm going to be a bit faster here because I've already explained the whole project, but in the whole process. But in this case, this is a renovation project. So this is an office in Berlin, and it was it used to be a shopping center, but the developer wanted to turn it into an office building again to make more money. So for that, they needed to change the, let's say, the facade so that the interior areas of the building could get more sunlight, and that was this kind of setbacks was their idea. And what we did basically, the approach here is different, right? Because we don't have different design options from scratch, but what we can do is to compare the renovated building with a virtual case. Imagine that this project could have been from scratch, right? Like what could have happened if the developer, if he could have just tore down the whole building and if he had built it from scratch again. So in this case, you can see that it's much more beneficial to renovate an existing building, and you can save a lot of basically CO2 emissions. And not only that, but you can also, they liked very much that we converted this difference here, because you see now that the renovative project, it was like 6,000 tons of CO2 equivalent, which is something huge. But if they had created the building from scratch, it could have been 16 tons, which is something even more huge. And we converted this difference into some savings in case that, okay, what does it mean in terms of flights from London to New York, for instance, or people refusing to eat meat from their diet, or people not driving their car. And you can see, for instance, that this difference equals to 10,000 flights from London to New York, or flights for 10,000 people at least. So and they understood those terms, and that's some publicity also for the building developer, and that's very nice. And of course, this in the upper right part, this is a 3D model that we used for our life cycle assessment. And what our input were basically the red parts. So the gray parts are the existing building, and the red parts are the new additions. And this is what results in this right column here. And now the last project, it's the Bojas Archive in Berlin. And this is a very interesting project, and the construction is almost finished. But this is different from the other projects before, because this is a singular building, or a so-called signature building, if you want. And well, in this case, I'm comparing two options here, but with these buildings, I mean, probably no one is going to tell you this, but if you have a signature building, right, which is kind of, it catches your attention and so on and so forth, the first thing that you have to realize is that its carbon footprint is not probably, is certainly bigger than if that building could have been built with, let's say, a regular geometry, right? With regular columns, regular slabs, and regular, let's say, structural systems. If you are doing this in this way, you are creating, you are producing a bigger carbon footprint. So the first design step could be, okay, how much more CO2 am I producing, and is it worth it for creating that building? And once you take the decision to say, okay, I'm producing more carbon footprint, but it's going to create a benefit for, I don't know, for the society or whatever. So let's go on with the project. And then you can now optimize it. So for instance, the original design was using reinforced concrete and composite columns for the whole building. And the design team of Bollinger+Grohmann, they came up with this optimized design using timber slabs and steel columns, which is more efficient, and they ended up saving 22% of the CO2 emissions in comparison to this original design, which is also nice, I guess. And this visualization with the Grasshopper plugin also helps see, well, first, if the last cycle assessment makes sense, And secondly, where are the so-called carbon hotspots that you might need to optimize in order to cut down the CO2 emissions. And finally, we have also been using this plugin at university with our students. And yeah, so what we do basically, we have this master course in summer, and we show them, let's say, an architectural design that they can use as a reference, and they have to use that architectural program, let's say, to come up with their own designs, but using our plugins, so they can compare different design options, and in the end, they can try to design for a low carbon footprint, and also combining the life cycle assessment with other, let's say, building performance simulations like energy efficiency, daylight analysis, sound insulation, room acoustics, and things like that. So we have this. I have just selected these two projects. So in the first one, the students, they design, let's say, a building out of bricks, which is not common nowadays, but they study different design options, and they realize that bricks are actually quite sustainable, and furthermore, you can reuse them if you build them properly. So that's also very beneficial, and it also means that you have a really nice, let's say, thermal insulation for your building and noise insulation. So that was very interesting. And the other design, it's a bit more crazy, let's say, because this group, they designed an office building that, well, it was, let's say, a mixed use, but not mixed use in different spaces. But in the first day hours, this could be an office building, and later on, it could become a residential building. So people could, let's say, occupy the office spaces that otherwise could have been empty, and that could have been a waste of energy. So with the simulation tools and life cycle assessment, you can very easily or quite efficiently calculate the carbon footprint at this kind of energy savings. Exactly. And well, that was the second chapter. And for the third and final chapter, we are going to jump into machine learning. This might be something new, or you might not be so familiar with this. So I'm going to start with the basics. But the idea is to use machine learning to implement cradle to cradle in early design stages. Okay, so the first question is, I've heard about machine learning, but what is cradle to cradle? So cradle to cradle, it means that our materials that we use for the project, so in our, let's say, the cradle of the project, the starting point, we are going, when the service life ends, I'm not going just to tear down the building, but I'm going to reuse these materials for the next building, which might be completely different. Of course, if those materials are in an adequate condition. And I have these two projects here. I have nothing to do with them, but you can see that they use they are reusing materials. So in this case, you can see these elements here that they were former columns or former trusses for a completely different structure. So you can see that this is quite irregular, but this is how they are using these materials. And the project on the right side, they are reusing, let's say, steel pipes, and you can see that they are connecting them in such a way that they now come up with this structure, which is a geometry completely different from the original project. So that what I want to say is that, okay, so you can see that they are using materials, and there is a certain logic in those projects, but they didn't use Grasshopper at all, which you can see, okay, but I see a logic here. Why I cannot use Grasshopper for that? And my conclusion is that traditional parametric approaches are not ready or are not enough for to optimize this reuse of materials, or to come up with, let's say, architectural geometries reusing materials like these two projects. So there's an assist that people are not using parametric design. So maybe we need to come up with another approach so that people can automate these design processes, right? And for that reason, I started researching into machine learning. And I'm going to start the basics, but I don't want to go very deep into this. So the definition of machine learning from the Wikipedia is the, one second. So machine learning is basically the study of computer algorithms that build a model based on simple data, known as training data, in order to make predictions, decisions, without being explicitly programmed to do so, right? That's the most important part. And well, this is the, let's say, the official definition, but the definition in 2023, machine learning algorithms are algorithms that use neural networks. And well, I think you are maybe not going to create your own machine learning algorithms, but I think you need to be familiar with these terms. So I have prepared this and this picture for that. So basically, what is an artificial neural network and how can we use that for machine learning? So first things first, the most simple unit of an artificial neural network is a perceptron, this picture on the left side. And basically, the idea is we have some input data, which is basically some numbers here. It can be just one number or some of them. And now our perceptron, it has some parameters, the so-called weights. So we have this simple operation here, this arithmetic sum of values from our input data. And then we have an activation function so that we have our data, and then we pass it through this function. And in the end, we come up with another numeric value, right? But the thing is that we have these parameters, the weight, and this other parameter, b. And if we have a neural network, we have several of these units in several layers. So in the end, it means that we have a lot of parameters, a lot of weights, and a lot of biases. And the idea is to use a very large data set, right, to train our neural network. So we have this data set of values that we know that are true. It might be images, or it might be just numeric data or whatever. And then we set our numeric parameters. We train our neural network so that when we input the input values of that data set, the output is right. So in the end, in the future, if we get a new input, I don't know, another image or another something similar to our training data, the output, the neural network is going to predict the correct output for that. Okay, so that's an introduction to neural networks. And now what can we do with them? I think I still have like 5 minutes, which is enough, hopefully. So there are different types of machine learning. You might have heard probably about supervised learning, the most typical one, right? I don't know, for image recognition or a prediction of, I don't know, prices or things like that. Now we have this ChatGPT algorithm, which is very popular, and that's something much more complex because it combines different machine learning approaches. And what I'm focusing on is on the so-called reinforcement learning. So reinforcement learning, we're using neural networks basically to train an agent in an environment, which is basically, in this case, well, a video game, but it is basically a problem that is defined as a decision process, right? And this intelligent agent, it trains and trains and trains, and in the end, he has trained so much that he's going to be able to predict the best possible action that will lead to the maximal reward, right? So in this case, this is like the snake game, and it knows at each step, well, after much training, if he has to go straight or if it has to turn in order to take the food, and not only that, also to avoid colliding with itself. And of course, that requires some, let's say, long-term thinking, and that's where the neural network comes. And but the idea was, okay, now I have these algorithms that work in Python, so I can either code them, but again, now we have the same problem at the beginning. If we have that in Python, we can code that, but for one project it's okay, but I cannot efficiently use that for different projects. So for that, I took a look into the machine learning plugins for Rhino, and I wasn't happy at all. So I ended up creating my own Grasshopper plugin, which is called Pack. It's also available in Food for Rhino. And it is the first Grasshopper plugin that implements the machine learning library TensorFlow into Rhino and Grasshopper. So you can use these very efficient algorithms to train your neural network. In this case, for supervised learning to predict data, and you can create more complex kinds of neural networks here, like convolutional neural networks to predict images, like those ones here. In this case, this, let's say, a standard database of handwritten numbers, but you can design your own, use your own images. And there are also more complex algorithms possible, like GANs or generative adversarial networks, in which the neural network, it seems like it's creating its own designs or its own pictures. It's similar to the DAL-E algorithm that you might have heard of, but well, much a bit simpler, right? Because I don't have the hardware that they have. And yeah, so basically, reinforcement learning is also possible with this plugin, which means that first we need to define, let's say, a problem as a sequential decision process, right? Which is something not, let's say, as you are used to in Grasshopper, in which you have just your parameters and your output or your result. In this case, you need to define this process, and for that, I'm using the plugin Anemone, and I don't know if I 1 second did I get a message here. I'm sorry, I think it's okay. So let's.
I think that was just like a brief message from one of the former students.
Okay. Okay. 1 second. Sorry. No. Okay, my cat got scared. You have to step down. Okay, sorry for the interruption. I'm back here. Yeah, so yeah, exactly. So now you can train your neural networks in Grasshopper for these, let's say, sequential processes. And this is the so-called DeepQ algorithm. And well, in this case, there are problems like the snake problem or the cardpole problem. And at this step, basically, you have the same number of actions possible. And these actions, it only works with a limited amount of possible actions, right? Like in this case, you can just go right or left or go straight. So in this case, it can work. But for more complex projects, you have a certain limitation. And for that, I also implemented this other algorithm, the Monte Carlo tree search. Well, in this case, it is not using neural networks, but it also solves sequential problems. So the idea is the same, right? And in this case, well, this algorithm is also used to solve very simple board games like tic-tac-toe and things like that, or checkers. But we can also use them for, let's say, one-player problems. In this case, you can use them like as brute force to solve the optimal path on a maze. But for such kind of problems with a variable, let's say, number of possible actions on this step. And I have not included in the presentation because I'm not done with that. But now my idea is to combine those two approaches, Monte Carlo research and neural networks, to come up with something similar to AlphaZero. I don't know if you have heard about that, but basically these guys that solve the game of chess almost completely, combining those two algorithms. And in a few months, it could be ready in Grasshopper as well to use this powerful algorithm for your own projects. And well, this is basically the the possible approaches and or the possible workflows. And now I'm using them for yeah, trying to the original goal, right? Trying to reuse elements in structural design or in architectural design. And this was our first proof of concept, so something really easy to design the truss geometry based on a sequence of numbers. So if you got a 0, you could define the next node. So we start from the left part, and if you got a 0, you locate the next node very close to your previous one, and if you got a 1, you got a big spacing. And with this kind of sequences, we can train a neural network so that they, if you have exactly, so if you have a stock of materials, so let's say we have these beams here or these timber and steel beams, it will come up with the optimal sequence to that lead to the lowest carbon footprint. And again, well, if we have some simple structures like that, you might say, okay, with parametric design, I can do something similar. But if this problem grows, we cannot use parametric design anymore because each step is one parameter more, and the complexity, as you know, it increases very fast. But with reinforcement learning, you can tackle these problems either when they grow in the number of steps or parameters. And in this case, I'm using the Monte Carlo research project because we have this bamboo hall that we designed in Guatemala. I also showed it in the first slide. And the thing is that we have the hall that has a big repetition of these frames, and we need to select the right bamboo stick or bamboo pole for each element, which depends basically on the nodes of each pole and the connections and things like that. But at the end, this algorithm can define the right sequence so that you find a pole for each element, and not only that, but that you avoid selecting one bamboo pole for your first column that in the end would have been optimal for the last element. So with these algorithms, you can train them so that you can basically select the optimal distribution for your structure. And the final example, well, it's a bit easier, but basically this arena, it was a project from one of our students, and she found this building that they were basically tearing it down. She said, okay, but the windows, there's no problem with that. So basically, we can maybe reuse this element for a new project. And for that, we trained also our neural networks in Grasshopper so that she could come up with different, let's say, Windows geometries, and the neural network, it could very easily decide a distribution of these former window elements. And that's also very interesting. But yeah, I think that was everything. I hope it was very interesting and it was not too much information. And if you have some questions, just let me know, please.
Okay, thank you so much, Deo, for this widespread presentation, like covering several topics. I think that the like trying to find out like something in common among the topics that you have covered are your computational design skills and your programming skills at the end. No? Like it's like you have a good background in this field and you can tackle several problems. No? So this is impressive. I don't know if there are some questions from the audience. Is anyone? If not, I will send you a Shailesh, go.
There was a LCA plugin. It was introduced. There was a comparison between baseline uh, about the carbon emission of the two buildings.
Exactly.
Yeah. So does it consider like cost parameter?
So a life cycle assessment, it does not consider cost. It just considers CO2, and this is basically the the variable that we're using in most of our projects because the cost is something that changes from year to year and month to month. So it's very difficult to to design a project, let's say 3 or 5 years in advance with that variable.
Okay.
But in one example, what we did is to combine CO2 and cost. So if you use a plugin like Octopus, for instance, you can combine CO2 and cost and optimize your structure that way. But that's something special, let's say.
Okay. Thank you.
You're welcome.
Yeah, go, Christian. Christian Dimitri, do you want to ask a question? If not, that it's gonna be me like asking a question. So I did a brief work on calculating the ecological footprint of several buildings like 15 years ago. Just like hi Christian, if you don't mind,
Yeah,
this is gonna be asking and then you go, okay?
sure.
So I did this like brief calculation on the ecological footprint of several buildings, just like using some very like basic spreadsheets. And at the end, the work that we did was to not just like compute the embedded CO2 of all the materials in the architectural design, just like taking into consideration their mass, let's say, but also some industry processes. So I mean, it's not the same. Just like to give you a silly example, okay? But it's not the same and a steel structure where everything is welded against a steel structure where everything is with pin joints, no, and screws and bolts. So my question goes in this direction. No? It's like, does your tool like allows to? I mean, it is like straightly linked to the mass of the architectural elements, or is there like a way to somehow like fine tune these results, like adjusting all the embedded CO2 of each solution, let's say, no more in terms of architectural design and not just in terms of like weighting your building.
Exactly. That's a very good question and a very complex one. But the idea is that in my plugin, I'm not coding the life cycle assessment, so that what I'm using is like the same that I did with the structural design, that is to use a third-party program, in this case, QuantKick LCA. And QuantKick LCA, it is the best and most powerful plugin for our software for life cycle assessment, and it's an external software. And in this software, you can model everything, not just the masses, but you can model the transportation, you can model the end-of-life scenarios, you can model anything. So the thing, that's the one thing. And the second thing is that, okay, but maybe in the first design stages, I'm just comparing options so that I don't know yet how the transportation is going to be or how the execution is going to be. And maybe that's not a big difference. So the first approach could be, okay, in the first stages, we do a simplified life cycle assessment, just with the masses probably and some simplifications. And later on in the final stage, we can take our model, calculated with our Grasshopper plugin, and the Grasshopper plugin has an option to get the results in Grasshopper, but it has a second option to export your model to the external program of QuantKick LCA. So you have the masses there, and in the web interface, you can model all sorts of things like the execution, like the transportation, end of life, and whatever you want. So that could be the more complex approach for those situations.
Mm-hmm. Okay, thank you so much, Diego. Christian, Dimitri?
I have a question regarding the machine learning cradle to cradle. Did you write from scratch the neural network, or you are using Python machine learning or a .NET library?
Exactly. So, well, my philosophy, once again, is to work smart, not to work hard, always at least, because in this case, it could have been very time consuming to code the neural networks from scratch. So the thing is that there are these very powerful machine learning libraries like TensorFlow or PyTorch that are from Facebook, Google, and other companies. But the problem was that they are in Python, and in the current version of Rhino, you cannot import those into Grasshopper because, well, there is a compatibility issue. Maybe it's going to be solved for Rhino 8, but it's not solved yet. So luckily, there are these other guys that have a lot of free time that created this GitHub repository that they translated the TensorFlow from Python to C#, and I used this library like TensorFlow for C# to implement that into my Grasshopper plugin. So basically what I did is to take these algorithms and put them into components in Grasshopper so that we can combine them without writing code. But yeah, I didn't create neural networks from scratch.
Nice. Impressive.
Thank you.
Nice.
Okay, guys, is there any other question? So,
I don't
not
have any.
Mac.
I don't have any specific question, but well, first, thank you so much to share all of what you did and what you created by yourself, and that's actually what I want to point out. Your approach of creating your when needed. That of course maybe your background or what you self-learned by yourself at another level, but it's really useful also for students or for practice to keep kind of a repository of your own tools that you created. They can be plugin or even tools or scripts to apply them later on. So I think it's really useful, and I can assure you that I'm using RFM Toolbox quite a lot. But yeah, I'm waiting for using also the back, but still missing some knowledge behind.
Yeah, I'm glad to hear that.
But really nice.
Yeah, thank you.
Okay, Diego, thank you so much again for accepting our invitation. For the current students, see you tomorrow. For the former students, keep in touch and stay tuned.